Problem 3. Rocket A has a positive velocity v of t after being launched upward from an initial height of 0 feet at time t equals 0 seconds. The velocity of the rocket is recorded for selected values of t over the interval between 0 and 80 seconds with data recorded in the table. Part A asks that we find the average acceleration of rocket A over the time interval between 0 and 80 seconds. Also, we are reminded to indicate units of measure. The central insight that we need to have in order to get going on this problem is the idea that the rate of change of a velocity is an acceleration. We are asked to give an acceleration in this problem, so we will need to be able to figure out the rate of change of the velocity. That rate of change of the velocity is the derivative of the velocity. With this table data, we will not be able to compute the instantaneous rate of change, but we will be able to estimate the rate of change. As stated in the problem, we need the average acceleration, and so we will have to compute an average rate of change. So now we are aware that we need the average rate of change of the velocity with respect to time as shown in the table. The average rate of change is for the particular time period between 0 and 80 seconds. The data points we will use are at the ends of the table. Putting those data points into the average rate of change formula, which you will recognize as the slope formula, is not a difficult task. Express the answer with units and you are good to go. It is possible to express the answer in simplest form, although on the advanced placement exam, an unsimplified answer is just as good as a simplified answer as long as the only thing that separates your answer from the expected answer is arithmetic. Also, if you choose to answer the question in decimal form, please remember to give your answer accurate to 3 digits after the decimal. In this case, the exact decimal value is 0.55, so it is not required to write any of the following zeros. Finally, as was stated in the question, please do not forget to write the units. Problem 3b. Using correct units, explain the meaning of the integral of v of t dt on the interval from 10 to 70 seconds in terms of the rocket's flight. Use a midpoint Riemann sum with 3 subintervals of equal length to approximate the integral. The math facts necessary to work this problem are: when you integrate a rate, you get an accumulation of the quantity in that rate. A Riemann sum uses rectangular regions to approximate the definite integral. Understanding the first fact, we can explain the meaning of the definite integral as the number of feet the rocket travels in the time interval between 10 and 70 seconds. In order to approximate this integral with a Riemann sum, we need first to find the requested subintervals. Since the entire interval of the integral covers times from 10 to 70 seconds, which is a span of 60 seconds, our 3 subintervals will each be of size 60 divided by 3, or 20 seconds. Those subintervals are here on the table. Visualizing this data in a scatter plot, we can see that we will be building 3 rectangles, each of width 20 but of varying heights. The heights are to be taken as the functional values at the midpoint of each interval. The midpoints occur at 20, 40, and 60 seconds, so we will use the velocities at these times as the heights of our rectangles. From the table, those heights are 22, 35, and 44 seconds. So we compute areas of rectangles which are 20 by 22, 20 by 35, and 20 by 44. The Riemann sum is the sum of those areas. With a common factor of 20, we can factor out 20 and complete the computation this way. The answer is 2,020 feet. Problem C. Rocket B is launched upward with an acceleration given by the formula. At time t equals 0 seconds, the initial height of the rocket is 0 feet, and the initial velocity is 2 feet per second. Which of the two rockets is traveling faster at time t equals 80 seconds? And we are to offer an explanation of our answer to this question. Since we are given an acceleration, and understanding that acceleration is the first derivative of velocity, we will need to anti-differentiate in order to find a formula for the velocity. First, we rewrite the acceleration formula as a power function. Then we apply the product rule for integration. Increase the power by 1, then divide the coefficient 3 by the new exponent and add c. Since 3 divided by 1/2 is 6, our expression is 6 times the quantity t plus 1 to the 1/2 power plus c. Now this is the kind of problem where the plus c in the antiderivative is critical. We were given information about the velocity at a certain time, t equals 0. Using that velocity with the time 0, we substitute the values of 0 for 2 for time, 0 and 2 for time and velocity into the general velocity formula we had developed and solve for c. We find that c equals -4. This allows us to get the particular formula for the velocity in terms of time. Note that there was information given in the problem which we did not use. Using the particular formula that we got from our work up to now, we could compute the velocity of rocket B at any time we wish. We use the formula to compute the velocity at t equals 80 seconds to find the velocity is 50 feet per second. Now the table contains the velocity of rocket A when t equals 80 seconds, so we can compare our computed velocity of rocket B with the given velocity of rocket A. Since the velocity of rocket B is greater than that of rocket A at 80 seconds, we can conclude that rocket B is going faster at this moment in time. In problem 4, we are given a piecewise defined function with a breakpoint at x equals 3 where the function rule changes. We are asked to determine if the function is continuous at x equals 3. Each of the two branches of the piecewise function consists of a continuous function, so the only question is about the continuity of the piecewise function at x equals 3. You might be tempted to answer such a question with an informal understanding of continuity at a point. In doing so, you might say, I graphed the function on my calculator and the two branches connected. While that does display some knowledge of the concept of continuity, it is not calculus. On a calculus exam, you will want to answer a question about continuity by referring to the calculus concept of a limit. In order to determine if the piecewise function is continuous at x equals 3, we need to know two things. First, in order for a function to be continuous at a particular value of x, three requirements need to be met. The function must be defined, the limit of the function as x approaches that particular x must exist, and the function value must equal the limit at the particular x. In order for a limit to exist, the limit from the left must be equal to the limit from the right. Let us see how our piecewise function measures up to these two requirements. First of all, the function value f of 3 does exist by the first function rule, which includes the case where x equals 3. Second, we can show that the limit of the piecewise function exists at x equals 3. The limit of the function as x approaches 3 from the left is computed with the first function rule. The limit of the function as x approaches 3 from the right is computed with the second function rule. Both of these limits can be determined by substitution, and both are equal to 2. By the requirements for the existence of a limit, that means that the limit of the piecewise function as x approaches 3 exists. Finally, we can state that the piecewise function is continuous at x equals 3 because the function value is equal to the limit of the function as x approaches 3. In problems of this type, beware of referring to the limit in your explanations. The term limit requires a function to answer the question, the limit of what? And using limit also requires a where, which is addressed in the part when we say, as x approaches some particular value. So don't say the limit. Always say the limit of what and where. Better yet, use limit notation, but be sure to make it complete by including the function, the where. In question 4b, we are given another piecewise function where the function rule changes at x equals 3. The challenge here is to choose m and k so that this function is differentiable. The first thing to realize is that if g is differentiable, then it is continuous. Just like in the part A of this problem, we can equate the limits of the function as x approaches 3 from the left and from the right. This is as easy as substituting 3 in the first and second function rules. Then, simplifying a bit, we have a nice relationship between k and m, although we don't yet know what they are. In another line of thinking about this problem, we note that the differentiability requirement here leads to the conclusion that the limits of the derivative of g as x approaches 3 from the left and right must be equal. Now, the first function rule can be expressed using exponential notation. Then we can use the power rule for derivatives to find the derivative of the first function rule. We need to compute the derivative of this first function rule so that we can use substitution to evaluate the limit of the derivative of g of x as x approaches 3 from the left. We see that this limit simplifies to k over 4. Meanwhile, the limit of the derivative of g as x approaches 3 from the right depends upon the derivative of the second function rule. This derivative is just the constant m, so the limit of the piecewise function as x approaches 3 from the right is m. Setting the limits of g of x from the left and right of 3 equal to each other, we get k over 4 equals m, or k equals 4m. We had previously found that 2k equals 3m plus 2, so substituting this new expression for k gives 8m equals 3m plus 2. We solve for m to get 2/5, and then use k equals 4m to compute k as 4 times 2/5, or 8/5. I just thought this looked cool. Hey, thanks for watching.